We are in the second part of the course, namely transfer phenomena, and in that we are in the second part, namely energy transport. So, this is the block we are going to start now, and that consists of integral energy balance, differential energy balance, of course the Fourier's law as well. And what is the scope of this lecture is the integral energy balance, both the derivation and the applications. Okay. That is why these are highlighted and this is also highlighted. Okay. What is the outline for conservation of energy, which we called as energy transport in the previous slide. Of course, integral energy balance equation, the derivation, and then the applications. Then differential energy balance equation, the derivation and the application. So, if you look at this 4 titles, it is almost analogous to what we discussed in for conservation of mass, conservation of momentum. Okay. So, in terms of the topics covered, they are very much analogous. There also we discussed about integral balance, differential balance, applications, similarly here as well. Okay. So, now we are going to discuss about integral energy balance equation. So, let us look at the outline. As usual, we start with the law of physics, and that is the first law of thermodynamics, and derive the integral energy balance equation from the first law of thermodynamics using the Reynolds transport theorem. In the integral energy balance equation, we discuss the rate of work done in detail, and then we simplify the integral energy balance equation, just we did for integral mass balance equation, and of course, finally look at applications. Now, what are the applications which we will be able to solve at the end of integral energy balance equation? Few applications are shown here, which we will discuss. First is finding out heat to be supplied. Suppose you have a gas to be heated from some temperature to some other temperature, what is heat to be supplied? Simple heater. Second is a compressor. Suppose you want to compress gas from some inlet condition to outlet condition, some temperature pressure to some other temperature pressure, what is the work to be supplied? Okay. So, these two are steady state examples which usually come across in a process calculation course. The idea is to connect what we had done in the earlier course with this course. The third example is little more involved. That is an example under transient condition. We have a high pressure line and a tank is connected to that, and it is getting filled. Okay. And it is a nice example where we see how to know the mass flow rate entering the tank based on the measurement of the increase in temperature. Okay. So, it is a transient energy balance. This probably would not have been done as part of a process calculation course. Okay. So, these two setups are well known to us. We have come across few times these two experimental setups, and what is shown are the control volumes over the two setups. In one case we have a pipe, and in the other case we have a tank through which there is inflow and then outflow. Okay. And the difference is that the first time when we came across and did a integral balance, we considered mass entering, mass leaving, okay, both in the pipe and the tank. Second time when we came across this setup, we focused on momentum entering, momentum leaving. Now, third time we are coming across the same setup, doing balance over the entire pipe or the tank, but now we will focus on the energy being carried by the stream. Okay. So, we look at what is the, let us say, enthalpy carried by the stream, the kinetic energy carried by the stream, potential energy carried by the stream. Okay. So, every time when we come back, we look at a different property being carried by the stream. Okay. So, let us start deriving the integral energy balance equation. As usual, the first step is the law of physics, and that is the first law of thermodynamics. Okay. Now, let us write the first law of thermodynamics, which is delta E is equal to Q plus W. Let us look at the nomenclature. Delta E represents the change in total energy of the system, okay, and Q represents heat added to the system, and W represents work done on the system. Okay. Okay. Now, what does it tell you? Whatever heat added to the system and work done on the system goes towards changing the total energy of the system. Few points to be noted. First, all terms refer to the system, and in terms of sign convention, heat added is positive, work done on the system is positive. Okay. For heat added, the sign convention is universal, but for the case of work done, the sign convention is not so universal. Work done on the system, we are taking as a positive, and what we will do now is express this first law of the thermodynamics in terms of rate with respect to time. So, what happens now? Left hand side becomes dE system by dt, right hand side becomes Q dot and then W dot. I will explain the subscript shortly. So, left hand side is dE system by dt, right hand side we have rate at which heat is added and then rate at which work is done on the system. Left hand side rate at which the total energy of the system changes. Okay. So, let us read it out formally what this equation tells us. So, left hand side is time rate of change of the total energy of the system is equal to the sum of the net rate of energy addition by heat transfer into the system and the net rate of energy addition by work transfer into the system. Okay. So, left hand side it is rate of change of total energy of the system. As usual, we have been very specific saying it is time rate of change, and right hand side we have two energy addition terms, one is by heat transfer, other is by work transfer. Okay. Of course, it is rate of energy addition by heat transfer and rate of energy addition by work transfer. It has a term net both for heat transfer and for work transfer. The reason is heat could be added or removed, work could be done on the system or by the system. So, net says it is net rate of heat addition and similarly net rate of work done on the system. This into the system and on the system are same. Okay. And so, now let us come to the subscript which I have used there. Net is of course representing as we have discussed now. This in represents heat added and work done on the system. Okay. In is used to say heat transfer into the system and work transfer into the system instead of out of the system. Okay. And of course, subscript system refers that we are writing for the system. So, very clear description of the terminology there in terms of subscripts. One is net, tells about both heat added and removed, net heat added taking into account the heat addition and the heat removal. Similarly, this net represents the net rate of work done on the system taking into account work done on and by the system. Okay. Okay. And now we will introduce terminology, we introduce a notation small e which is capital E per unit mass. Okay. What is capital E? That is the extensive property of energy, and if you divide the extensive property by mass you get the intensive property of energy. So, when I say energy, it represents sum of all the energies per unit mass, namely internal, kinetic and then potential energy. So, capital E represents the extensive property energy, and per unit mass if you divide you get the intensive property energy. So, this energy here means and of course, we have internal energy per unit mass, kinetic energy per unit mass and then potential energy per unit mass when you divide by m. Okay. Now, when we derived the Reynolds transport theorem, we introduced the extensive property in terms of integral given by this expression, and we also wrote the rate of change of extensive property in terms of this integral. Okay. Just to recall system quickly, so that we can easily understand. This example we have seen several times as an example for system. We have a cylinder at time t equal to 0, the gas inside the cylinder is identified as system. At some time t later, if you open the valve, part of the gas escapes, but the system still consists of the gas remaining in the cylinder and whatever has escaped. Okay. That is the system. Okay. Now, in the present case, capital B represents total energy which is E. This total represents extensive property. This energy represents sum of all the 3 energies. Okay. So, we can even say total energy, first total for extensive property, second total for sum of all the 3 energies. Okay. And the extensive property here is capital E, and if you write in terms of the intensive property, it is m into small e. Okay. And we introduced small b as the intensive property. In this case it is energy, which is total energy per unit mass, and in our nomenclature it is small e. Okay. So, now what we will do is write down this expression for the present case where our small b is small e. Okay. Small e is total energy per unit mass. And how do you write that? Instead of capital B, we have capital E system, which is small m into small e system. How do we write this? As we have done few times earlier, we split the volume of the system into smaller and smaller volumes, okay, and that is delta V I, and each volume can have its own density, its own energy. Once again want to mention, E represents the sum of all the energies per unit mass, and to get the extensive property for the entire system, sum over all the volumes, and then we take the volumes smaller and smaller. We consider an infinite number of such smaller volumes, okay. And so delta V, the volume of each region goes to 0. So, in this limit we can express the summation as this integral. What this means is, you are allowing for variation of density and the energy within the system, and rho into dV is the mass and E is the energy per unit mass. So, when you integrate you get the total energy of the system. Okay. Okay. So, now let us write down the first law of thermodynamics in terms of rate, which you have written in the previous slide, and then now let us express the E system in the left hand side in terms of this integral expression. So, d by dt instead of E system I have this integral expression, of course right hand side is same. Why do we write in terms of this integral expression? Now you are able to express in terms of the usually measured properties, namely rho, and what is E? The internal energy per unit mass, kinetic energy per unit mass, and then potential energy per unit mass. So, by expressing in terms of this integral, you expressed in terms of usually measured or known variables, namely density, internal energy, velocity, elevation, etc. Okay. How do you interpret this equation? This is the first law of thermodynamics for a system, as we have seen here, made of fluid particles. Okay. That is the way we should visualize. We usually apply first law of thermodynamics for a let us say a gas inside a cylinder with a piston which goes from one state to another state, etc. The way in which we should visualize this is, it is the first law of thermodynamics for a system and made of fluid particles, and the system is flowing. That is why we have expressed this first law of thermodynamics in terms of rate. Left hand side also it is rate of change of energy, right hand side rate of heat transfer, rate of work transfer. Reason for expressing this is first law of thermodynamics for a flowing system made of fluid particles. That is how we should visualize this form of first law of thermodynamics. Okay. So, let us rewrite that equation. Okay. So, now we will use the Reynolds transport theorem, and this is a general form of Reynolds transport theorem for any intensive property B, which relates rate of change of property for the system and to the rate of change of property for the control volume and net rate at which property leaves through the control surface. Now, for the present case, B is equal to E, sum of all the 3 energies per unit mass. So, let us rewrite that equation replacing B with E. So, now how do you read this? Left hand side is rate of change of energy for the system, right hand side rate of change of energy for the control volume, and net rate at which energy leaves the control volume through the control surface. So, now what are we going to do? In the left hand side of the law of physics, we are going to use the Reynolds transport theorem, so that it gets expressed in terms of control volume and control surface. Okay. We are doing it the third time, first time for mass balance, second time for momentum balance, now for energy balance. So, now in this form, the left hand side tells about rate of change of energy for the control volume, okay, and the net rate at which energy leaves the control volume through the control surface, right hand side still in terms of system. Okay. So, we will have to express this for the control volume. Okay. Okay. How do we do that? Let us rewrite that equation again. To express the right hand side in terms of control volume, we have discussed the concept of coincident control volume and system. What does it mean? At time t, we consider the system and control volume to be coincident. That is shown in 3 different ways here as earlier. In the derivation of the Reynolds transport theorem for the simple geometry, we took the control surface and system boundary at time t to be coincident with each other, meaning that the control volume and system are coincident with each other. Second way of representing the control volume is shown here. We could consider a system which is just entering, which is partly outside, partly inside. We could consider a system whose boundary completely coincides with the control volume, or a system which is partly leaving the control volume, which is partly inside partly outside. What do we choose? We choose a system which is coincident with the control volume, so that it gets well defined, its boundaries are well defined, which is same as that of the control volume. And in terms of our animation, so these are different possibilities for the system. We consider the possibility where the system just coincides with control volume, okay, and that is the instant we consider, okay. And we consider the case where, so different possibilities for system are there. We consider the case where at time t the system and control volume coincide with each other, okay, fine. So now what happens? The right hand side, which is for the system, now becomes that for the control volume, okay. So the subscript now changes, still remember it is net in both for the heat transfer term and the work transfer term, but system now has been replaced with control volume. So let us now write down the complete integral energy balance equation, where all the terms now correspond to the control volume. So left hand side we have the rate of change of energy for the control volume, second term is net rate at which energy leaves the control volume through the control surface, and now right hand side net rate at which heat is added, and then net rate at which work is done on the contents of control volume. So like to mention, we have done this system to control volume the third time. In the case of mass balance, the right hand side was just 0. In the case of linear momentum balance, it was sum of all the forces acting on the system. Now in this case it is the energy added term, namely by heat transfer and work transfer, okay. This system to control volume change is more clear in the case of momentum balance and energy balance rather than the mass balance, because we will be replacing 0 system with 0 control volume. We may not understand very clearly at that point of time. Now having done 2 more times, for linear momentum balance we replace this sum of forces acting on the system by sum of forces acting on the control volume. Now similarly here, net rate of energy addition by heat transfer and work transfer term for the system has been replaced for the control volume. So now it becomes clear how we go from system to control volume, especially from linear momentum balance and the energy balance, okay. Okay, so let us write down the integral form of energy balance equation, which we have derived in the last slide. Now what is the significance of each term? Okay. Left hand side, the first term tells about rate of change of total energy within the control volume, more specifically time rate of change of total energy within the control volume, okay. And next term tells about net rate of flow of total energy out through control surface by convection. Remember, total energy here means sum of all the 3 energies, okay. And right hand side, what does it represent? The first term represents net rate of energy addition by heat transfer into the control volume, okay. And of course next term on the right hand side gives the net rate of energy addition by work transfer into control volume, okay. So left hand side we have the transient term, the first term is the transient term, and then the second term on the left hand side is the convection term, and right hand side we have the heat transfer term and the work transfer term. And we should note that it is into the control volume based on the convention which I have discussed earlier. Okay. And this term by convection has the same meaning as we have discussed earlier for total mass balance and momentum balance, but now the quantity of interest is the total energy, or the property which are focusing in this balance equation is total energy. Okay. So, let us have an comparison between all the integral balance equations which are discussed so far. That is the integral mass balance, okay, and that is the significance. Let us write down all the equations and look at the similarities between them, okay, and of course, what are the differences as well. Okay. So, that is the integral total mass balance equation and the significance. Now, let us write the integral linear momentum balance, of course, in the x direction, it is a vectorial equation. So, let us write down the equation in the x direction, okay, that is the significance. And of course, right hand side is not 0, it is sum of external forces acting on the control volume. So, let us write down the integral energy balance equation which we have derived now, that is the right hand side, and just now we saw the significance for the first term on the left hand side, then the convection term, and then the net rate of energy addition terms on the right hand side by heat transfer and work transfer. Okay. How do we discuss all these equations? To better understand them, we will have to keep in mind the control volumes which we have seen earlier. So, all these equations can be applied for control volumes drawn over entire equipments shown here for experimental setups or for physical geometry like this. Okay. Writing total mass balance, momentum balance, energy balance over the entire equipment where there is inflow and outflow. Okay. Now, if you look at the first term on the left hand side, okay, all of them tell about the time rate of change, of first equation for mass, second equation for momentum, the third equation for total energy. So, all of them tell about the rate of change of mass, momentum, energy within the control volume, well known to us as the rate of accumulation term. The second term on the left hand side tells about the convection term. We have explained what we have discussed what a convection term is. Whatever is carried by bulk flow by a stream, suppose if you have stream entering and then leaving, whatever property carried by this stream is the convection term, and as we discussed now some time back, the stream can be looked upon as carrying total mass, momentum or energy. In fact, total mass, momentum and energy, and that is what is reflected by the second term on the left hand side. And of course, as per our sign convention, all of them are net rate of flow out through the control surface. What is the property? It is total mass here, linear momentum here, and then total energy here. Okay. But all of them otherwise, look at the Bay as written, the words are all same, only the property alone changes. Here again net rate of flow out through the control surface by convection, here again net rate of flow of total energy out through the control surface by convection. The terminology has been maintained the same, the property changes from mass to momentum to total energy. Now, coming to the right hand side. So, left hand side is very much analogous, a transient term and a convection term, one which accounts for whatever is change happening within the control volume with respect to time, and one which accounts for whatever is taken in, taken out. Right hand side the terms are not same for the case of because the law of physics is different. For the total mass balance it is 0, for the linear momentum balance it is sum of external forces acting on the contents of control volume, and for energy balance it is net rate of energy addition by heat transfer and work transfer into the control volume. The right hand side terms are of course they are different, but left hand side terms are all very analogous. If we keep this in mind, becomes very easy to understand all the integral balance equations, okay, and the relationship between them as well. And this viewpoint that if you look at a stream it carries total mass, momentum, energy, that viewpoint helps us to write the especially the second term on left hand side, because that is by convection, okay. And if you look at the tank and then say that mass could change, momentum could change, or energy could change respect to time, then that explains the first term on the left hand side. Of course, right hand side depends on the property for which you are writing the conservation equation, and that could be 0, it could be forces, or could be energy addition, okay.